Earth Science time. Today we are talking about, let's title it Early Earth. I'm going to do it in blue. Early Earth. So if you could please have your notes out, write down the title Early Earth, blue and green, because guess what? Earth. Blue and green. At least now it is. Why? Why Earth is blue and green? Are the other plants blue and green? Early Earth. So we have, we got modern Earth. Modern Earth. Blue and green. Early Earth. What color should I select from my tray of colors for early Earth, you reckon? You can see the colors I have to choose from. For early Earth, what color should I select? If you had to guess. Red, he's going to guess red. I don't have red, so would you please try to select colors I do have? Orange, okay. What shape? Blob. Like this? No, not really. Why? This is actually important. I know this seems silly to you, but this is actually important. Why not that shape?
Because gravity.
Gravity. There we go. Okay, so there's step one. You, as a writer, should write down gravity. So why Earth, right? And I'm going to highlight for not the first time, but certainly also not the last time, that when you ask questions about why, there can be a couple different answers. So without getting too deep into it, could there be a supernatural answer to this question? Why Earth? That's a yes or no question. Could there be a supernatural answer?
Yes.
Yeah, there could be. But guess what? Science is concerned with nature, right? The observable, what's the word I'm looking for? Tangible, right? Things that we can see and feel. Science is concerned with nature. And again, that is not to say that nature is superior or that science has the superior knowledge, but science is only concerned with things that are disprovable. And the supernatural, by definition, is not. And so could there be a supernatural answer to the question, why Earth? Yes, there could be. But that's not what science is concerned about. And so when the question is why Earth, the scientific answer, that is the answer based on physical evidence, is gravity. How did it start? Again, could there be a supernatural answer? Yes. But scientifically, the evidence suggests, how did it physically start? Gravity, before there was an Earth, there was proto-Earth. Let's write that word down. Proto-Earth. What does the prefix proto mean? Before or early. Before there was Earth, there were, I'm just going to draw these little dots here. What do these represent in your estimation? I've got some various sized dots. They represent proto-Earth. And what are these things?
Asteroid.
Yeah. The word asteroid we use specifically to mean those rocky bodies within what we call the asteroid belt. But yeah, you're not wrong. They're rocky bodies, smaller rocky bodies. And then due to the influence of gravity, they start to coalesce. Have you ever heard the word coalesce?
No.
The word coalesce, I'm going to put coalescence as a noun. The word coalescence means they come together. Well, I tried my best, but it's, I think, C-O-A-L-E-S-C-E-N-C-E. What do these arrows indicate? In general, when I could probably find an actual mathematical, I'm going to estimate 80% of the time I draw arrows on this board, those arrows represent what? That's too specific, and no.
Motion.
Sometimes, and so maybe I'm going to reduce the percentage to like 60%, but usually on this board, at least in my drawings on this board, arrows represent forces. What specific force now? Gravity. So the force of gravity pulling them together under their mutual attraction. The reason this is a hard thing for people to wrap their heads around is this is outside of our daily experience, right? If I have, I drew 20 dots here. If I have 20 objects in this room, there are about 20 chairs in this room, we don't observe on the daily basis that those things coalesce under mutual gravity, right? Wouldn't it be crazy if every morning when I came in this room at 7:40, my chairs had all gravitationally attracted into a ball? That would be crazy. We would be amazed by that because that's not how we see things working in our daily life. objects, for gravity to be noticeable, objects must be very large. And so if we're diagramming Earth here, each of these objects is maybe the size of a United State, right? Like maybe this one's the size of Wyoming and this one over here is the size of Connecticut. But these are very, very large objects collapsing under their mutual gravity. That's another word I'm going to use. Collapsing under their mutual gravity. What's the word mutual mean? If you've ever been texting a girl, you probably know what the word mutual means. What's mutual means?
There's others.
Yeah, well, it goes back and forth, right? So like if you and this girl you're texting have a mutual attraction, that means you're attracted to her and she to you. When these are mutually attractive, it means that this one is attracted to that one and the reverse, and they're all attracted to each other. And so they're collapsing under their mutual gravity. Yes?
Why doesn't the asteroid belt collapse into one planet?
That's a fantastic question. So how come, I love that question, because if we say that the evidence suggests that this is how Earth began, and we see this in reality now, like I can look, I mean not right now because the sun's shining, but tonight I could look and find probably maybe Ceres, which is an asteroid in the asteroid belt, with my telescope. And with stronger instruments, we can see many, many more objects. So how come, is the question, if this exists in the solar system today, does it not do this? Right? The answer is, again, gravity. And I was trying to think in my head of a way to make you answer your own question, but, well, maybe I'll still try. What else is going what's going on around the area of the asteroid belt in the solar system? What are some things, what are the neighbors of the asteroid belt? Do you know where in the solar system? Jupiter and Mars. It's in between Jupiter and Mars. Can you guess how one of those answers might affect this?
Because the gravitation from those two planets is too strong.
Yeah, that's exactly right. You could go as far as to say entirely Jupiter. Like, you're technically right that Mars does have an effect on it, but it's 99 point some numbers % because of Jupiter. So because of the gravitational pull of Jupiter, specifically because of the tidal forces of Jupiter, which is something we'll talk about later on in the year, but because of the gravitational pull of Jupiter, this cannot happen with the asteroids. They can't coalesce under their own gravity because there's an external gravity field removing that possibility from them. So evidence suggests, I'm going to make a little list of evidence here. Evidence suggests that Earth, proto-Earth, collapsed from these smaller objects under the effect of mutual gravity. What evidence? Is one of the pieces of evidence that I'm going to write down that we went back in time and we witnessed this with a video camera? Obviously not. So we can't use that. So we have to, what in general in geology do we use because we can't go back in time? Yeah, last time we called it uniformitarianism, right? Remember the idea that the things that are happening today have been happening for all of history. So what could we use as an evidence for that? If we can't go back in time and see Earth form, what could we do instead?
The layers of Earth.
Okay, I'm going to put that. That's not the one I was looking for from that question, but yeah, layers of Earth. We'll talk more about that in a second. What else? This one, you had a question about this on your chapter review yesterday. Earth's what?
Oh.
That's the layers, but that's not the one I was talking about. You had this question about where did the something of Earth come from? And there were 4 answers. And it said which one was not a source of Earth's.
Oh.
It's okay. I already wrote it. It's heat. Earth's heat is another piece of evidence, and we'll talk more about that in a second. I'm looking still for the other one about uniformitarianism. We can't go back in time and see how Earth forms, but we can
look out into space.
Yeah. We can observe planetary. I'm going to put extrasolar. What might that mean?
Super far out.
Yeah, away from the sun. Solar means referring to the sun, so extrasolar means outside of our solar system. So observe planetary formation outside. We can directly observe other planets forming in other solar systems. And when I say directly observe, we observe their gravitational effects. We don't actually look in a telescope and be like, oh yeah, a planet just formed. But we do observe their gravitational effects. one other main one, a big one that we talked about, I think in the last lesson too. I'll put Earth's. Could we use the fossil record?
Yeah.
Not for this. Why?
No.
There weren't.
There weren't animals.
Yeah, there wasn't life yet, so we can't use the fossil record. But well, it's slightly different. If we can't use the fossil record? What's the other record we have?
Relative age dating.
Yes, in combination with, which is one of the relative age datings, in combination with.
Rocks.
Yeah, there we go.
Oh.
I'm going to put rock record because that's what I was looking for, and I think that's what you meant, the rocks. But we do, you're right, use relative age dating to say these are the oldest for such and such reasons, and then we use absolute age dating. I'm going to just indicate those two, relative age and absolute age dating. By the way, remind yourself, what are the absolute age dating techniques? The main absolute age dating technique is radiometric. There you go. So I want you to see how well these evidences work together. So this is the evidence. And by the way, this is pretty much the only class that I list the evidence for, because a lot of times, maybe if people aren't skeptical, it's at least that they're not aware of how the evidence works together. But all of these evidences point to the same thing, right? We look at the layers of the Earth, and we see exactly what we would expect to see if it formed in this way. And that's one thing. That's its own kind of idea. But also we look at the Earth's heat, and it has lessened, its internal heat has lessened to the exact amount we would suspect if this were true. And we look at how long and how many extrasolar planets form, and that gives us within the range of the same exact principle that this is how Earth formed. And we look at the rock record, both relative and absolute age dating, and we find that all of this taken together gives us the same answer of about 4.3 to 4.5 gigaannum. Remember what gigaannum means? Billion years. So about 4.3, about 4 billion years ago, it is supposed, I'm going to phrase it that way because the evidence suggests that, but could it be otherwise? Sure, it could be. But the evidence suggests that it was about 4 billion years ago, Earth, under mutual gravity, the material that makes up Earth coalesced to form the early Earth. And how would that have been? The ancient poet says, Earth was without form and void. How would Earth have been back then? Again, was it this? No. Why? We already answered this question. Because of gravity. So Earth, when it first formed, would have been spherical, because all massive objects under their own gravity become spherical. And it also would have been mostly what state of matter? Liquid. So mostly liquid and mostly rock, right? But liquid rock. So what we call magma. And this was the time of Earth that we title, do you have your chart? Does anyone still have their chart? I should have said, does anyone not still have their chart? Because I have extras. So during this time, from about, actually this chart lists at 4.6 gigaannum, so I'm going to change the 4.5 to 4.6. 4.6 gigaannum. What do we call this time? I said it in the last lesson too. Lesson also. Looking at our chart, what do we call that oldest time period of Earth? From the beginning until about 4 billion years ago. That's true, but that's not the best answer. So all of this is Precambrian, or what I sometimes pronounce Precambrian. And we'll talk about what that word means in a second. But more specifically, what eon is it?
Archean?
No? Try again. Older.
Protozoic?
Nope, older. On the very bottom. Hadean. So we call it Hadean, which means, do you remember, like what? Like hell. Yeah, exactly. Hades is the Greek for hell. I'm going to put like Hades so that when an adult walks in the room, they don't think I'm writing bad words on the board. So like Hades. In what way?
It was hot.
Yeah. Everything was on fire. Actually, fire itself couldn't exist because fire, as you understand, it needs oxygen, and there just wasn't that. But everything was molten rock, right? Everything was thousands of degrees, and everything was molten rock. And just like your lab, Cody, because it was a liquid, the different liquids stratified into different layers. And so all the denser liquids sunk to the middle, the iron and nickel. And I shouldn't say all, but most of the denser liquids sunk to the middle. And then less dense liquids, and then less dense liquid, and we end up with this layered version of Earth. And just like your Alka-Seltzer tablet, what would the lightest thing in these layers be? Yes, but what kind of substance? We said it was all liquid rock. That's not quite true. Some of it was solid as it cooled, but also some of it was what? That would be by far the lightest. Gas, yeah, just like your Alka-Seltzer tablet, right? So the early atmosphere formed. Now, over millions of years, as the Earth cooled, and we get into the Proterozoic eon, through the Archean and into the Proterozoic eon. So we had Hadean, and then the Archean, and then the Proterozoic. And as the Earth is slowly cooling and slowing, when Earth first formed, it was spinning fast enough that the days were 6 hours long. And as it, or what we would now call 6 hours long, and as it cools, it also slows. And in the Archean and the Proterozoic, we have this thing that happens called, and this is still the Precambrian, by the way. We're going to talk about the Cambrian in a second. Actually, this lesson is going to be through the Cambrian. There's one big event that happens here. So while Earth was still, as I said before, without form and void, what's this arrow represent? Again? What do arrows represent on this whiteboard? Force. What force, probably? Gravity. And this is the planet Theia, what has been now named the planet Theia, collides with early Earth. And just, have you ever seen a lava lamp work? Mine's not on. I should have turned it on for this lesson. But have you ever seen a lava lamp work? A blob blobbles up, and then maybe it runs into another blob, and then they both kind of fuse into one bigger blob for a second, and then a little baby blob is born. So these two wreck into each other, and a little baby blob is born. And that little baby blob is what we now call the moon. So that's and what do you think is the evidence that the moon formed in this way? There's really two ways we witness moons forming even now. Can you guess what one of them is? When we look at other planets and see them gain moons. What's one way? The only way that I know of that we have observed other planets gaining a moon is by what? Asteroid capture. An asteroid, not necessarily an asteroid, again, like your thing before, but some outer space rock body captured by gravity and just starts circling, and now it's a moon. That's one way. And the other way, the way that it is supposed that the moon formed, is that, like this, a piece of this planet comes off and becomes this moon. And why do you think, can you guess the evidence? I shouldn't say guess. Can you infer the evidence that tells us that our moon formed this way as opposed to being a capture?
It's got the same.
Exactly right. Exactly right. Very good. It is, as we look at moon rocks, they are the exact same chemical makeup as the majority of Earth rocks. And so that tells us that they came from the same source. So that happened during this time of the Archean and Proterozoic. And also the other thing that occurred here is what we call, I'm going to move over here now, they're called the Great Oxygenation Event. So, by the way, life had started at some point here. And no one knows how, and it is impossible to know how life started. There's several hypotheses. One's called panspermia, which maybe, it's kind of just like passing the buck, but maybe life actually started on some other object and then came to Earth on an asteroid or a meteor or something. That could have happened. I mean, is that feasible? Sure, that's feasible. That could have happened. There is some research being done into lightning strikes on nitrogen compounds causing early RNA molecules. In fact, it has been shown in the laboratory that with the right amount of electrical current, inorganic compounds can fuse to become very similar to RNA or even protein compounds. And so could that have been it? Maybe. Could it have been the old idea of what we used to call the primordial soup, where there was just a hodgepodge of different chemical compounds and they accidentally formed life? Sure. Could it have been something supernatural? Of course. The point is we will never know how life started on Earth, but I'm going to ask you a very simple question. How do we know life started on Earth?
Because we're here.
Yeah, because there is life on Earth, right? And so at some point, the fossil record shows that somewhere in this time, the first life began. The earliest single-celled fossils are from this time. So it's almost impossible that we have found a fossil of the oldest life form, but the oldest fossils we have are from this time, and so that tells us that life started somewhere between Hadean Earth and now, and these times when we have the earliest fossils. So at some point life started. By the way, there was life, and eventually that life changed enough that these stromatolites, maybe the most important organisms to ever exist. Like we kind of puff ourselves up and say, oh, look at me, I'm a human being, I can change my environment. But maybe the most important environmental change organisms to have ever existed are these stromatolites. They're colonial cyanobacteria. What's colonial mean? Okay, I think you're going off like the idea of colonization, that sometimes cultures colonize other cultures.
No, I was going off from.
Oh, okay.
Is a stem cell.
Okay.
They turned into like mounds.
Yeah, that's exactly it. The colonial meaning they work together. They are, as a calling, they're existing as multiples. I shouldn't say work together probably, but they exist as multiples together. And the cyanobacteria can perform what very interesting and at this time almost unique task? Photosynthesis. And as you know, the chemical equation from biology for photosynthesis is that organisms can take CO2, by the way, from Earth's early atmosphere, very rich in CO2, and water, which, how did water get on planet Earth? This is another little side note, but where did that come from? Something like, we see the asteroid, but many other asteroids and meteorites. We see, when we look even at the spectral lines, which is how we tell what's in solar system bodies, of other meteors and asteroids and things, we see that a lot of them are made out of water ice, especially comets are made out of water ice. And so the thought is that early in Earth's history, there were a lot more of these little guys floating around, and as they bombarded Earth, they carried each with them a little bit of water. So water came to planet Earth in that way. And the carbon dioxide from Earth's atmosphere and the water that came from the bombardments combine in photosynthesis to form sugar, which these organisms also use to build their cell walls, and a byproduct, which they don't use in photosynthesis, oxygen. And so during the time of the Great Oxygenation Event, Earth's atmosphere goes from, I would guess, less than 10% oxygen to much more than 20% oxygen. So these are such successful organisms, they literally change Earth's atmosphere forever on a large scale. I mean, your existence changes Earth's atmosphere forever, but these things as a group of organisms change it on the large scale forever. And one of the pieces of evidence for this, especially that it happened at this particular time, about 3 billion years ago, is that all over the world we find of this age these iron deposits where, you know, that iron oxide, rust, does not dissolve in water. And so the iron that was dissolved in the oceans, iron salts dissolved in the oceans, like iron chloride, for instance, dissolved in the oceans, combines with oxygen that is brand new in the atmosphere. And all over the world there is this like falling out of rust, what we call banded iron formations, where the seasons cause different amounts of iron to be deposited. And that corresponds to the Great Oxygenation Event. So the main events in the Precambrian, by the way, this Precambrian ends at the Cambrian period during the Cambrian explosion. It ends at the Cambrian explosion, which is where the life, which was mostly single-celled and the multi-celled organisms were very simple, in a very short or relatively short geologically period of time, explodes. It's not a literal explosion. It's not boom, but it's an explosion of life where before there were only single-celled or a very few multi-celled organisms, and in this very short geologic time, their life rapidly diversifies into almost all of the groups of organisms we have today. Things with vertebrae, the arthropods, plants, all this stuff develops in the Cambrian explosion. And so before that, we call that time the Precambrian, which, by the way, this Cambrian explosion happened about 500 mega annum. It's about 540, million years ago, 540 mega annum. So everything from 4.6 billion years ago, when the Earth formed from mutual gravity, until 540 million years ago, so for about 4 billion years, there was life, but it was single-celled, and the biggest events were the formation of the moon, the cooling of the Earth, and this great oxygenation event. Do you think there's a lot of fossils from this time, from the Precambrian? Not really. Why? I can think of 3 reasons. You think there's a lot of fossils from the Hadean? No, because it was magma. I'm not aware of any. There might be some. That's not really my area of expertise. But if there are, they are also, the other reason is that they would all be what? Or almost all, except for the later times, single-celled, which you can imagine the difficulty in finding single-celled fossils. And just the sheer fact that it was so long ago, erosion, right? Remember uniformitarianism. Things that are happening today have been happening for all of Earth's history. Erosion has been going on. They would be very rare by now. The rocks from this time are very rare, and they're much more resistant to erosion than fossils generally are. And so for those 3 reasons, we don't find very many Precambrian fossils, and the ones we do find, we're very lucky if they're high quality. But that's one of the ways we know. That's one of the pieces of evidence is the fossil record. The other main one is the rock record. Do you have questions about any of this? I feel like that's a pretty robust rundown. I want to make sure that I hit all the topics I wanted to hit. Your book does talk about prokaryotic and eukaryotic life, but as long as you are aware of what those terms mean, you should remember biology. I think you should be good. Do you have questions about any of this? The 3 main things to remember, the 3 main events: great oxygenation event, the distinct separating into layers, which wouldn't have been an event so much as a long-term process, and the formation of the moon. Questions? Okay, and I will end with, could there again have been a supernatural cause or guidance or even complete refutation of this? Sure, that could have happened, but in science we focus on the physical evidence, and this is what the physical evidence suggests. Could it have been otherwise? It almost certainly was otherwise, but this is what the evidence suggests. Something is probably wrong, but that's what science does, is we do our very best with what we have, and then later on when we find out what was actually the truth, we change it. That's a strength of science, not a weakness.